Good evening, everyone, and thank you, Dr. K.V. Sriram and Professor Dr. Renuka ji, for giving us an opportunity. Just a lot of new students are attending today's session. So just for their information, NXP India is conducting NXP Campus Connect program, and the purpose of this program is to share new technologies in the field of VLSI and the system engineering. On first Tuesday every month, we are sharing updates related to the VLSI technology. All the sessions are related to that. And on third Tuesday every month, we are going to share the topics related to the system engineering. Today, we have a session on CMOS design, and our presenters are visible on the screen. But before jumping on to that one, we have a senior member of India leadership team, Mr. Yogesh Mittal, who is our senior director for verification and validation. Maybe Yogesh, welcome to this platform and share few thoughts about NXP India and a brief, thank you for the MIT management for this.
Sure.
Over to you, Yogesh.
Okay, thank you, Manish. Can you hear me?
Yes, go ahead.
Okay, so good evening, everyone. I would like to welcome Manipal faculty and students to this initiative from NXP India team. We wanted to bridge academia and industry through this platform. So I would like to welcome all of you to this learning platform. And I would also like to thank Manish and the entire team behind this initiative. It's very easy to get lost in the corporate job, but I really appreciate how the teams are taking extra time to reach out to our young minds and prepare them to be ready with the latest and greatest in semicon industry, and so that by the time they get some job and they start working, they are ready with whatever is the latest coming from the industry. And I would like to apprise why it is important for you. If you look at the McKinsey reports, semicon is going to be 1 trillion industry by 2030, and most of it, or a lot of it, would come from India. So it's very important for young engineers in India to be trained to be the best in the world. And last week, our CEO was in India. He met Mr. Modi, and both the leaders talked about how we can enable India to be in the forefront of semicon technology. And we talked about the Campus Connect initiative and how these kind of initiatives can really make students learn things beyond their textbooks. So this is the platform where we talk about system engineering, we talk about IPs, how do you design the SoCs, the low power aspects, the analog design, the digital design. So if you really want to learn about this semicon industry without getting a foot into this, this is the platform where you guys need to be really serious. It comes every 2 weeks, and the time is like 5 p.m. and you will get all this communication from your faculty, and I'm sure that you guys will like it. There are various topics. Feel free to give us feedback if you feel that we need to include specific topics which can benefit all the students. But at the end of it, remember, this is the platform for you, and we are just enablers. So your feedback is very important. And I would again, welcome all of you, and best of luck for learning on this platform. That's all from my side. Thank you, Manishi. Back to you.
Okay, thanks Yogesh ji for the nice words, and very motivating for students to learn and share the thoughts with other students to attend this session. Very important for them in their career. I think we have Professor Dr. Renuka. Welcome, ma'am, for this platform. Maybe a few words from your side.
I thank the NXP team for conducting the Campus Connect program. So very glad to hear that maybe students get benefited from this. I'm just representing the computer science department as a HOD on the team. Thank you.
Wow, ma'am. Thank you. Thank you, ma'am, for the nice word. And I think share this information with other departments also, so it will be useful for other departments also. This is our regular, program, and fortunately happening, on every first and third Tuesday regularly. And the session which we did in the past, the video recordings are available. Maybe, we'll share the links for that, so that please share that links with other, students and colleagues. Thank you with that. We have Vandana Narula, she is our expert from the CMOS design, having 15 plus years of industry experience. And we have Pramod Gaikwad. He is also, our expert on the CMOS design, having 15 plus years of industry experience. Over to you guys, Vandana, a brief introduction of yourself, and then start the presentation. Over to you, Vandana.
Yeah, thanks, Manishji. So hello everyone and welcome to this session. So I'm leading efforts in PDK in the NXP India. And PDK, basically I have a 15 year of experience in PDK, plus I also have 8 years of experience in Foundry. So I closely work on failure analysis and chips in the Foundry, and global experience in USA, as well as Australia. So over these years, I have been basically we are enabling different technology nodes for the supporting the designers in NXP. And I have been from the educational background. I have done MTech in material science and physics honors from Delhi University. So yeah. So please, Pramod, please help to introduce yourself.
Yeah, so myself, Pramod Gaikwad. I do have overall industry experience of 15 years, and first initial 5 years I worked on the RTL design, SOC integration, IP verification, then memory compiler qualification. Then from last 10 years, I'm focusing on the standard cell library development. So in the second part of this session, I will be covering on the logic libraries part. Yeah, from the education background, I do have a MTech in various design and embedded systems from Mysore, VTU University. Yeah, over to you, Vandana. Thank you.
Thank you. So let's get started. And so basically in this presentation, we will be covering over two parts. Part one is on PDK, and the agenda is to have a brief outline of the VLSI design flow, important terms we used, PDK, what is content of PDK, and the different components. And part two will be taken over by Pramod, and he will be having over introduction to standard cells, how it fits in the ASIC flow, the library development flow, a different kind of standard cells, and as well as the standard cell library qualification flow. And then we will have some time for the Q&A session as well. So let's get started over the PDK. So PDK, as we understand, it is a very basic backbone of the all the technology enablement we have to do. And all through this process of VLSI design flow, different component of PDK are used. So just a brief outline, what is the design flow? We have a logic synthesis followed by physical design. The logic synthesis, it converts an RTL to a gate level netlist, and the physical design takes that netlist and converts it into a real chip with each step where it optimizes the timing, area, and power. The different stages that involved in this in the VLSI design flow include the floor planning, where we take the aspect ratio of the design and where we try to fit in different blocks or macros in the chip or the core area to optimize on the area and delay. Then we have the placement to actually decide on the location of standard cells in the circuit. The constraints have to be met so that there is no congestion or timing violations, and the wire length is minimized. Then we look at the CTS, which is a clock tree synthesis. Herein, the the topology of the clock network is decided, and clock has to reach the each sequential element in the design while minimizing the skew, power, and noise. Further on, the design goes to the routing stage, wherein the different connections are established, keeping in view multiple constraints. The constraints are the timing, DRC, LVS, and to minimize on the interconnect length. For the after the routing stage, if some physical sign off or timing sign off, etc., need to be met with slight variations, they can be taken care using the engineering change order, which is called ECO. And then the after this stage, we come over to where a GDS file is available. And after that, the GDS, chip finally converts the GDS to a manufacturable chip, which is the product that is outputted. The different terms that we use in our flow are fab, as you know, which is a fabrication where the IC chip manufacturing is done. There's a process team which owns a device, and they are responsible of how the device work, how the what are its characteristics, and they provide all those inputs to the model team and the PDK for the enablement and support. The design enablement, it constitutes of multiple collaterals, which include PDK, IO, standard cell memory, and all these combined components make the DEC, which is the design enablement configuration. This configuration has all these component, and this is the first input for the design team, which actually work on a product, and they take input from all these different collaterals, and they make a product out of it. The different aspects of our PDK also include the DFM, which is the design for manufacturability. The DFM is meant to reduce the cost and make the product more manufacturable and reliable. The as you know, there is an ESD, which is the electrostatic discharge. This is a sudden surge of current between two charged objects, and it is very detrimental to the electronic circuits, as it causes the dielectric breakdown and has a big impact on the yield and quality. So throughout the process of the chip designing, care is taken so that the ESD protection is available and we do not get into the ESD problems. Sign off is the stage where we have the series of verification steps that happen, like DRC rule checks or DFM checks, and they are done with incremental fixes and retesting so that the design is signed off. During the fabrication of the chip, there are multiple layers, and if they happen to have a misalignment, then it causes different failures to the chip. So the silicon alignment is taken care by foundry to get rid of these problems. And there are also DFT, which is meant to increase the manufacturability of the product. It introduces different test structures and fault models in the chip so that the issues are caught early on rather than on the silicon. And after the chip is taped out, we further review it through the silicon validation to look for any kind of issues or that happen. And they are the once the issues identified, the workaround is provided to cause a to improve on those issues. Going into now the details of PDK. So PDK, basically, as we saw, that it is the backbone to for the designer to go from the RTL to GTS2 stage. It constitutes of the multiple inputs, which is primitive devices, models, design rules, process information, and scripts. They have the foundry provided rule decks, which are which provide the different DRC check, DRC or LVS check criteria. The PDK can be used as modified or can be as is. So as is whatever the foundry provides, or it could be customized for certain product needs. With the increase in the technologies and technology node going over to FinFET or smaller technology nodes, multiple new flows and processes are introduced, and they kind of uh, help to increase the PDK quality. Excuse me. This is um, this is the design stage, whereon we go from specification, architecture, schematic creation, spice simulation, then layout, then DRC and LBS checks. Excuse me. We also go through the post simulation stages to go on the area and timing closure. After the sign off, DRC and LBS are done, and the design is available in the GDS2 form. IC tape out can happen, and design can go for silicon testing. Excuse me. There are different PDK inputs. The inputs could be come in the form of the process, so layer, via, or grids and constraints. We also have the information from the device level support, which comes as device parameters, their connectivity information, their models. From the there are also litho rules and multi-patterning support, and the design style or design intent, which is the input to the PDK. And there is multiple tools and flows that are supported, which constitute what is goes as an input to creating a PDK. As we see in the PDK development cycle has one collateral, which is more of like a device information, which comes from the design rule manual. The device specification that is come from the device owners in form of its characteristics, its behaviors, that is also incorporated in the models. And the multiple multiple physical verification checks are incorporated. During the development, we also have a excuse me. We also take into input the technology file, the DDF container, which is parameters, netlist, or the device information, the PCell parameters, as well as the different testing that is happening on the design, which is like DRC checking, LVS checking. And there's also testing on the component level, which includes the QA cells, the all cell test case generation, or the different IPs that we test on the regression basis. So this is a flow of the how the PDK is developed. Then the outputs constitutes of the different rule decks, which is the DRC, LVS, or extraction. PDK also provides supports to the simulation in the form of different views, models, interface, and the netlister support. The devices in the PDK come in the form of the parameterized cell, which is P cell. There are multiple callbacks which are in the PDK to actually see the different values of the width, length, and their interdependence onto some other layout parameters. PDK also provides the support for the parameters and the symbols. In addition, the process containers contains the layers and the via. There's a LEF and the technology LEF, as well as the display.drf, which is in the Virtuoso, how the layers look like. And in addition, there's a GDS to OA map files to when the designer want to dump out a GDS and share it with the foundry. So all this, in addition to the this validation flow, constitute of the output of the PDK. The in terms of the process constraints, The PDK, as you know, is highly dependent on the foundry. So whatever the reliability information comes in from the foundry, they are the basic constraints to the PDK. Whether the PDK is what kind of level of certification is available for the reliability rules, what kind of technology specific information is available. So like the different for the FinFET, there are special requirements for the technology specific information. And then from the tool perspective or the flow perspective, there could be selected flows which are also dependent on the kind of process node that a PTK is supporting. In terms of devices, all the basic devices are part of PDK, which include the resistor, capacitor, BJT or MOS. And then the device structures must be approved by the process team, and the parameters, symbols, callback, and layout, they all come in the category. Then for the compliance check, basically there are multiple checks that are basically must do for a PDK. Or a design to be manufacturable. This includes that there should be layout versus schematic check, design rule checks, antenna rules, packaging rule, extraction, and DFM rule checks. The rule decks, they basically contain what are the rules for these components. So the criterias are that the design functionality and the reliability specs should be captured here. The technology and the foundry specific information is specific to a particular technology node, and they are part of that rule deck. For the mask layers, as we understand, the GDS to OA map files and the different kind of layer information, this all constitute of the this mask information. And for the design rule manual, basically there's a information on the reliability, there is a guidelines or different DRC rules. They all constitute the DRM. That is a design rule manual. Coming over to why DRC is important. So basically, the DRC is important so that the chip is manufacturable and there are no open short or antenna happen during the lithography stage. There's no reliability issues because these issues are very they cause a huge loss, and the product kind of profitability is completely damaged. So in order to have better yield, better robust product, the DRC is must. The kind of rules that are there's some basic outline that we provide here, that what are the minimum width checks. So basically a width, it is a minimum or the inside edges of the distance between the two inside edges. There are spacing checks between different single same layer or the different layers. So this is a distance between the outside edges. The notch is a single connected shape, but these are the external edge pairs which form the notch. And the overlap, which is basically the common distance between two overlapping polygons. So these kind of checks are part of the DRC rule checking. Then there are multiple layers that are formed during these in these rule decks, that we have say original layers which are overlapping. Then based on those original, there could be some layer operations which cause these derived polygon shapes, and we can have both the polygon layers as well as the edge layers here. So these are the edge layers, and there could be the error layers. So like if some space checking or the width checking is done, so then we could form these derived error layers. Going over to the flow of how the DRC works. So basically we have a layout database, which is the input. It has there are multiple layers that are defined, and then based on those layers, multiple operations happen which output the derived polygon, derived edge, and derived error layers. And in order to if there are multiple operation happen on these layers which are the derived layers, then further they are outputted to the DRC result database. So the design has a .gds and these DRC, these all layer operations form the DRC rule deck, and we have a DRC result database. Now going over to the second type of check, which is the layout versus schematic. So layout versus schematic is very must that it actually captures what is the whether the intended functionality is implemented on silicon. So the kind of device, suppose the intent was to form an inverter, however we formed a buffer. So then the complete functionality is ruined. And then in addition to just the functional behavior, it also checks whether there are any open or shorts in the design. And also the LVS forms a base to go over the next stage of the design phase, which is the extraction. And this gives us an annotated RC netlist. So whenever we have a rule deck, it actually constitutes of multiple operations which end up recognizing and forming connections. It defines a stack, like whether, like for the interconnect, we have a metal 1, via 1, and metal 2. So that connectivity is also established in the LVS deck, and that helps to recognize the devices, the interconnects, and also it attach names to the extracted nodes. And then the this extracted circuit netlist is then compared for the reference netlist, which is from the schematic or the which is our design intent. So the data flow that goes for LVS is that we have a layout, we go through the connectivity extraction, we form the devices, so device recognition, and finally it goes to the comparison phase where the layout versus schematic is checked using this as a source spice, and then the results are that it dumps out an LVS report showing what is a match or the mismatch results. Then we go over to the stages of extraction, which is that we have a like, as you know, that as a technology shrinks, the interconnect delay get dominant over the gate delay, and the interconnect can cause lot of delay in the circuit performance. So basically, this extraction phase give us our interconnect delay, and for this this is very crucial step for time giving the extraction results. They also give input to the timing closure. So in the extraction, we have different corners for extraction. And different corners are formed taking into account the process variation. The process variation can be of different forms. It can be a systematic or a random variation. The systematic variation happens through the different processes that happen in foundry. It includes the CMP or the copper erosion. So basically, CMP is the chemical mechanical polishing, where there are tables that are written into the interconnect technology file to define metal thickness as a function of density and width. And likewise, there's a bias applied in the interconnect technology file to replicate what is seen by foundry at the OPC as the OPC bias. And based on those OPC bias values, the resistivity of the metal is decided by the line width. So these kind of the variations of all these different parameters are captured in different corners. Then why it is important, why the parasitics are important? It is important because there are multiple checks that, as we saw in the physical design flow, we have to pass through all the different stages of EM checks, self-heat analysis checks, ST analysis, and crosstalk or SI. And if we have very huge parasitics, we can end up violating our power specification. We can cause a we can cause increase in the local temperature, which is captured through the self heat analysis. We maybe end up having timing violations, which is captured through the ST analysis. And then the IR drop may be really poor, so this is captured through the IR drop analysis. And again, the signal to noise ratio may be really bad, so we need to catch it through the SI or the crosstalk analysis. The kind of qualification that is done in the PDK is we have different kind of testing. So this is all device testing, IP regression, unit level testing, We also have a automation test suite to do the kind of something like a QSL. So different parameterized cells, their different width, length, and different parameters are varied to catch on the issues in the device development. And then it is followed by the kind of tools and flows the PDK is supporting, as we saw that, like, there could be the MIR flows, the extraction, the LVS, and then finally everything is bundled together to check on the completeness of the PDK. So thank you. This is I cover the PDK part, and then Pramod will be coming over the logic library portion.
Yeah. Thanks, Vandana. Please let me know whether my screen is visible.
Yeah, it's visual for me.
I hope you're able to see only one screen, right? The two monitors are there.
Only one.
Okay, great. Yeah. So in this session, right, we'll be covering on the standard cell libraries, also called as a design development kit. This all starts with as Vandana said, once the PDK team delivers the respective models, using those models, we will be generating the standard cell libraries that will be in turn used by the SOC team. So as part of this session, we will be covering all these different topics, starting from this introduction to the standard cell, where exactly this will fit in the ASIC flow, then what are the different steps involved in the logic library development, and then the different types of standard cells, and how do we do the qualification, then so end it with the conclusion part. Okay, let's start with the introduction. So, if you see this particular picture, right, you may recognize like there are three different types of walls there. One is with the, say, red brick, another is with the stone, the third one is the fort, where the stones have been used to form the wall. So out of all these three pictures, the one common, the important thing, if you notice, right, all these three walls have been constructed with different types of bricks over here. So one might be using a concrete block, one might be using a tile press kind of different blocks. So in the similar way, the way these bricks have been used or the stones have been used to form the fort, right? In the same way, using the standard cells, we can construct the sock designs. This is the standard cell, and in fact, in the standard cell also, we do have a different tracks there, like 6 track, 12 track, 9 track, and based on the speed, the power, based on that criteria, we may either go for one of these track cells. So in general, starting from the device, we will be creating the circuit, then we will be drawing the layout. So those layouts will be in turn used to form a die, and that will be fabricated in the IC, and that will be used in the system, and this will be used in the relevant application. So in summary, you may say the standard cell are the basic building blocks for a physical design, and this is the one of the schematic view and the layout view for a simple AND gate cell. And this do contain the different cells. Actually, we do offer the combinational, sequential, multiple cells over here, and which are present in the different VT variants, the HVT, SVT, LVT like this, and it's also available in the different track. So as part of the standard cell libraries, we do also provide the different EDA views, which will be used in turn in the SOC design flow. So in summary, you may say like the standard cell library contains the different track height and different channel length based on whether the leakage is reducing, the power is needed, and the gate oxide thickness like GO1, GO2 devices, then the different drive strength, the drive strength 1, 2, 3, 32 like that. And then the variety of the EDA views will be providing. So these EDA views are nothing but say dot leaf for the timing information, the left which will be used for the physical design as part of the router tool, and the OpenX database which is needed for the analog design if they want to use the standard cells in the analog domain. And this is the Verilog view which do contain the behavioral information. And this is the ATPG basically the used for the DFT purpose. and then the Red Hawk. So this is just a couple of views. I just put it in the board, but in practice, we do provide a lot of other EDA views based on whether our SOC designer is using, say, Synopsys tool or Cadence tool or Mentor tools or the Apache tools. Based on his application, we have to support those EDA views as part of the standard cell. So in summary, the standard cells are really highly reusable, and we don't have to spend again and again time on constructing these things. And because these are readily available and those will be used in the soft flow, we will be seeing the drastic reduction in the overall design time. So this is the short introduction about the standard cell. Let's see where exactly it will fit in the soft flow. So I would say, like, starting from the RTL, you might have heard the word called the synthesis, which will convert the RTL into the targeted technology. And when they say the targeted technology, this is nothing but the standard cell representation. So you see here the flip-flops, inverter, and gate, and this will be later converted into the respective layout views. So this is the one which is finally fabricated on the chip. And once we have this collection of standard cells, those will be placed in this kind of a PNR in the different rows here. And then based on the RTL description, the netlist description, we will be doing the stitching of those standard cells. So output of the inverter should be connected to AND gate, means here one of the standard cell, assume this is the inverter, this should be connected to the NAND gate. Something like this, all the routing will be established. And this routed routed design, we call it as final GDS, and that will be sent to the fabrication for the final manufacturing. So this is like an overview, but let's have a little bit detailed look here. So this is the starting from the design specification to the RTL coding. This is the conventional ASIC flow, and as you see in the right side picture, this is the abstraction of those designs. So for example, when designer says like I need a IC for a car or some mobile or some other applications, the design team will start doing the RTL description. They will start writing the RTL code, and later they will do the synthesis and convert that into the gate level netlist. And those gate level netlist has nothing but standard cells, and that will be containing the transistor information. And that will be later we'll be having its equivalent layout that will be fabricated in the manufacturing. So this is the kind of abstraction level. The deeper the abstraction level you go, the more costly it is. For example, if you do some mistakes at the RTL description and if you fix it, it's very economical. But if you make some mistake on the mask layout, and because it got fabricated in the fab level, and if you found some issues, the fixing it calls for a huge money, and it's a big loss for the company. So we have to be very careful as we go down the abstraction. So let's have a look at the little bit different way. So during the RTL coding itself, the designers will use these standard cells like sync micro cells, level shifter, based on whether they have different voltage domain or not, whether the clock domain is crossing or not. So based on those applications, people use this standard cells as part of the RTL coding. And once they migrate, I mean, even if you don't use this RTL code, I mean, these cells in the RTL code, but later anyway, as part of the synthesis stage, you will be converting the RTL into its equivalent library. So in equivalent library is nothing but these bricks basically. So you can consider this as a standard cell. And these are the different EDI views. Maybe for that purpose, just put a one more slide over here. You can see like these are the different EDI views. For example, the Verilog and VAMS model will be used for the functional simulation by the SOC designer. And the .lib, which will be in the LVF format, as well as the left file, those will be used by the ST analysis tool to do the timing analysis. So similarly, the different views will be used in a different purpose over here. So this is the one overall summary. And now let's start with how exactly we will develop the standard cells. So these are the different steps. We start with the design specification. So whenever there is a need of the cell, designer like the one who is doing the RTL coding, or maybe the custom, those are our customers, right? They will ask us like, I need a so and so functionality. Let's assume I need a AND gate. So we'll ask those information as part of design specification. We will define those stuff, and then we'll start with the Verilog modeling. Basically, we'll study whether the behavior behavior, whatever customer has expected, is it really the one which we are coding here or not? So if at all there is any confusion or any differences in terms of the Verilog model and the expected specification, we will get a clarity on that part. And once the functionality is well understood with the help of Verilog, we will go with the circuit design. Then we will draw its equivalent layout. From the layout, we will do the extraction where we will extract the resistor, capacitor, those sorts of parasitic information. And that extracted netlist, later we will use it for the timing view generation. So this do contain all the area, leakage power, internal power, delay information. All this will be part of this timing section. And also we'll be using those extracted netlist for the UDFM, like for the DFT purpose. Also we will use that information. And also based on the customer, whether if the designer wants to use the Red Hawk data, we will use that view for and generate the Red Hawk associated EDA views. But if it is a Olters or some other EDA vendor, so associated views we will be creating. Now let's start a little bit deep into the design specification. So how do we consider the new cell request, and how we what are the different parameters we should be focusing when we design a new cell? So starting from the cell function, we will ask what is the targeted technology we have to develop this cell, what is the VT, what is the length of the device, what is the power, performance and area requirement, and what are the different tool vendors, whether we are going to support only Synopsys, Mentor Graphics, Cadence, Apache, Red Hawk. That way we'll be asking what are all the tool vendors you are going to use these cells, and then the different EDA views you needed, and the different process voltage temperature specific PVT points. So we will collect all such information as part of this data sheet. And then one of the key input we will check with, as Vandana explained, we will check with PDK whether for a given technology, whether the PDK is supporting all the DRC, LVS extraction rules or not. So we'll be having a close interaction with the PDK team. Then once the design specification is understood, there are some background will be there. For example, if you see this snapshot, I have taken it from the TSMC web. And as the year progresses, we are now in 7 nanometer, 5 nanometer, 3 nanometer stuff. So there are certain advantages with moving to the later and latest technology. Those I'll be covering in the next slide. So when you compare the 28 nanometer versus 16 nanometer, so basically the 28 nanometer uses planar CMOS based technology devices, and the 16 nanometer uses the FinFET devices. So as you know, the FinFET will provide the better leakage benefits as well as the area. So looking at the graph, you see like compared to the 28 nanometer, in 16 nanometer, we do get both the performance advantage as well as the area is almost reduced by half. So that way we'll ask designer whether which technology you are interested, whether it's the 28, 16, 5, like that. And then comes the within the different VTs over there. For example, HVT stands for the high VT, ULVT stands for the ultra low VT. So what is the exact difference? HVT. Yeah, sorry, there was some background noise. Okay, HVT stands for the high VT device. That means this device will take a little bit more time to switch on. That's the reason the performance wise HVT is slower, while it is taking more time to switch because of the high VT. In terms of the leakage, it offers a very reduced leakage. So in the same way, the ultra low VT do offer the speed advantage. However, it is not good from the leakage perspective. So based on the leakage performance, we will decide which VT we want to design the cell. And looking at the leakage alone, earlier in the technology starting from 180 nanometer up to 28 nanometer, the leakage component was a significant portion of the total power. However, in the 16 nanometer onwards, because of the FinFET benefit, we do see the leakage component is drastically reduced compared to the total SOC power. So looking at the next slide, as I said earlier also, we'll be having a different height also. It's like 7.5 track, 9 track, 10.5 track. So the advantage with the 7.5 track is the cell height is very small. That means the area wise it is a very small. Since area wise it is small, it is not good from the speed perspective. So that's the reason you see like the area wise the ultra high density will fall over here, but performance wise it is not that much good. But if you see the high speed 10.5 track library, it is very good because in terms of the speed. However, because it is the higher track, it consumes the higher area. So that's the reason in the rotated area, if you see the high speed density cells will fall under in the right side, but the performance wise it is better. So based on whether the performance or the area benefit, people will select which track they want to proceed. So this is about the design specification and how do we select the cell. Now let's start with the behavioral modeling. So as part of the behavioral modeling, we want to understand whether the desired cell functionality is correctly defined or not. So we do use the different Verilog types over here, starting from the Verilog, Power Verilog, VAMS Verilog. If this VAMS Verilog is especially used for the analog mixed signal applications. So if you see this slide, for a simple AND gate, we will declare what are the different inputs, what are the different output, and what is the functionality of this cell. And for again for the flip-flop, what are the different input output as well as the cell behavior. And also it do contain the timing section also, which will be covered as part of the SDF back annotation from the verification team, which is needed. So here, once the Verilog models are available, we have to ensure like by toggling all the power pins and other stuff, the functionality is still meeting our expectations or not. For example, if you take a complex cells like a state retention power gating cell, so those SRPG cells do have two power supplies, and whenever one supply is toggled down and toggled up, we have to still see whether the cell is retained its previous value properly or not. So for all those purpose, the power Verilog is very, very important. And also when we create the associated other views, the schematic and the spectre.lib, we have to ensure like the functionality, whatever we have defined in the Verilog is exactly same as that of the spectre behavior also, as well as in the .lib also, we are getting to see the same functionality or not. So once the Verilog model is ready, then we will go for the circuit design. So the circuit design consists of three different key area. We have to first ensure the functionality wise we are up to the mark, whether the for all the input combinations as well as the power pin combinations for the given all the PVT combinations, the cell functionality is coming as per the expectations or not. And in terms of the robustness, there is something called process mismatch parameter as part of the random variations, whatever Vandan has just covered. We will be running the Monte Carlo simulations and ensuring like for all the PVT conditions, my design, my circuit is working nicely or not. Then there is a reliability aspect where we do the aging simulation, considering the hot carriage injection, bias temperature, those things. And then the key parameters where what we are targeting is the functionality, delay, leakage, and other items over here. So one typical example, if you see, this is the circuit assume we have, and is the process block, which will be delivered by Vandana's team. And basically the PDK team will deliver the process block. And also we will give the in the control file, what is the process, what is the voltage, what is the temperature, those sorts of information we provide. And we will configure the tool, whether I want to do the transient simulation, delay or leakage. And then we will be observing the output. So this is the typical waveform for the one of the inverter input output characteristics we are studying, along with its VI, the DC transfer characteristics we are studying over here. So once these parameters are studied, we do also focus on the beta. So what is the right width we have to select for the PMOS and NMOS? So the functional beta means we have to focus mainly on the area with the functionality is the most important and with the least average performance. Whereas in the balanced beta, both the rise and fall transition, the delay values should be exactly coming as same. So these are very important from the clock cell design point of view. The tapered beta is the one where if we have multiple input output path, we want to have one output as a rise favored, another is the fall favored. There we will be using the tapered beta ratios. So from the low power design perspective, we notice that the PMOS and NMOS, those behavioral change as we operate the cells at the lower voltages. That means if you design any, say example, the clock cell by considering the one particular voltage, it is not guaranteed that it will work in the same way in the other PVT conditions. So that part we have to take care. And also we have to study the signal to noise margin ratios. These are very typical stuff which you might have already studied in your, I think the second year or third year CMOS VLSI course syllabus actually. Yeah. Now, once we have the beta ratio, if you take the one of the planar technology, we do notice that for the given inverter, we will be having the NMOS and PMOS because of the mobility reasons. You know, like the PMOS width will be higher compared to the NMOS in the planar technology, and we'll be having the beta ratio in a range of say 1.4. And when we increase the drive strength from drive strength 1, 2, 3, 4, the beta ratio will remain constant over here. Yeah, so this is in the planar technology, but from the FinFET technology, the number of fins what we use that will determine the NMOS and PMOS width. And normally these NMOS and PMOS width will remain same in case of the FinFET technology. So another slide is on the beta ratio, but this is on the NAND cell. Again, here you see like the beta ratio is remaining same for the different drive strength. However, yeah, for the higher drive strength, the beta ratio may differ also. So this is the one of the consideration of the beta ratio in the circuit design. Now just moving to the layout design. So once the circuit is finalized, now we have to draw its equivalent layout. So if you see the slide, we do have two types of technology comparison over here. One is the planar transistor and another is the FinFET. So in the planar technology, as you know, there is a limit on how much gate we want to reducing here, starting from say 90 nanometer, 65, then 16, the 90 to 65, then 28. But further down, if you start reducing this thing, when the device is in off state, this gate is no more able to control the leakage current over there. So that is the disadvantage with the MOSFET, which is addressed very nicely with the FinFET, where the channel has been covered in a three-dimensional way with the gate. So here in the FinFET technology, the gate has a very nice control on the complete channel, and that is the reason when the device is in off state, you see the leakage will reduce drastically. So this is one of the biggest advantage with the FinFET, along with its other advantages, including the short channel effects are less and the area is less, like that. So if you see the slide number 61, so this is the one typical layout diagram for the planar and FinFET devices. So using the planar, like this is the transistor width and this is the NVEL with the PMOS, and below is the NMOS configuration, and its equivalent is in the FinFET. So where assume this is here, the three fins are there. So we are constructing the similar inverter over here. And in the complete right side of the picture is the actual representation where the gate is shorted from both NMOS and PMOS, and the pin A is formed there, and the drains have been shorted, and the pin Y output has been taken. So in case of the FinFET, again, these horizontal stripes, what you see, these are the fins, and more or less the other arrangements will remain same. For the some manufacturing reasons, they put some dummy poly over here at the edges of the cell. Otherwise, the middle one is the actual gate connection. So this is on the FinFET, and if you see within the FinFET, it's possible to have a 3-fin as well as 2-fin as well as the 4-fin structures. So in the compared to 6-track and 9-track, if you see the differences, the 9-track cell do offer the benefits in terms of speed and performance, because it do offer the 4 fins running in every devices here compared to the 6-track where only 2 fins have been used. No, this is the one more way of looking at the key parameter, which we are now discussing. This is on the how do you decide the spacings basically? How do you define the the layout grids, pictures, like that part? So here there are three variables will come into picture. One is line to via, and via to via. So when you focus only on the line to line by giving the 0.6 micrometer spacing, and assume you have done this kind of a construction, and if you want to place the via, then line to line via placement is not possible. So you can place the via only after one line gap here. So this is the one of the limitation with this structure. But if you follow with the line to via architecture, here it's possible to put the via compared to one more via, but with the gap of one line. And now if you go with the via to via architecture, here we can place all the three vias side by side. So based on whether you want to restrict to here or this thing, out of 1, 2, 3, we will go for the cell architecture decision. Normally we always go with the third option, where we'll ensure like via to via spacing is also met. Now is the next interesting point. Assume once you develop the standard cell, and assume this is the cell 1, cell 2, cell 3, like inverter, NAND, NOR, and all these three cells do contain the VDD and VSS information. Now you can place those cells in this fashion, like this is the one row, second row, third row, and all the VDDs you can short it here, and you can put some gap over here, and all the VSS you can short and you can put a gap here. So if you do so, it's marked it as an incorrect way, because you are wasting a lot of space over here. So instead, the recommended way is we have to flip the cell. For example, assume this is my TB is my one of the inverter cell, which has the VDD and GND, and this the mirrored BT is a NAND cell, assume. Then we have to flip that cell, and then we have to ensure like this cell's ground and the top level cells ground, those are shorted together. So thereby by flipping the cells, we can abut this kind of stuff, and we can form the cells like in the properly. We can place the cells in row 1 and row 2. Similar, this is just one example, but we do have a standard cells where the single height cells itself, this is a single height cell, and this is a double height, and this is a triple height, and the quad height. So based on the cell complexity, when during the layout design, we have to take care whether we'll be designing those cells in a single height or a quad height, like that. So looking at the slide number 66, this is the left file. So you can call it as one of the EDA view. And what is the need of this left file? So this left file is abstract information, which contains only abstract information. Basically, it's kind of a very small information which is needed for the top level router, because the layout do contain so many other information like poly, diffusion, and so many things which is not needed by the PNR kind of a router kind of a utilities. All they need is the connectivity information, where these connections are happening, and this is the OBS sections as well as the pin positions. Only this much information is sufficient for the router tool. So that is the reason we provide this left as one of the view. And this left when we delivered, when the SOC team starts using that, for example, this is the one standard cell, and within the standard cell, assume we have used the layers up to M1, and you want to make a connection from one standard cell to another standard cell. So how do we do that? We will put a M2 layer in a, say, horizontal direction, M3 in a vertical direction, M4 again in horizontal, and again vertical. So that way we will be making a kind of different state, the kind of a pillars we will add, and we will make the connections. And for a given technology, the PDK team will define what is the possible layers which we can use. And at the standard cell level, normally we will restrict our usage to only say M1 or up to maximum M2, so that the SOC design teams, when they start abutting the cells from one cell to another cell, they are allowed to use the M3 and above routing layers. So this is how the top level connections will happen at the end of the day. And you can also consider like you might have seen a lot of flyovers, right? So there will be one road, and you will take one pillar, and you will make a one more flyover on the, and again if you take one more pillar over there, you can make a one more road. So in the same way, in during the CMOS, the physical design also, during the routing also, the same thing will happen. And higher the layers, the resistance will be lesser here. Now, once the layout is ready, then what is next? So we have to see what is its impact in terms of resistance and capacitance. So we do we do extract the resistance capacitance information from all the layers which is used in that particular device. Now, once you make a initial schematic, and if you dump that information in a textual format, we call it as a circuit description language. This is a CDL language, and it do contain only the information about what is the MOS, what is its width, length, and there is a PMOS, NMOS, only that information, as well as the connectivity conductivity information will be there, but it don't contain the parasitic information. But what exactly mean by parasitic? So if you closely observe this layout, because of these different source, drain, the number of fins, gates, and the higher level of metals, whatever we are using, each of these layers will constitute certain amount of capacitance as well as the resistor. So in the right side picture, you see there is a resistances have been extracted, and the above picture you see there is a capacitance have been extracted. And those resistance and capacitance information, we will model it as part of the netlist. So here is one of the video I took from the Cadence. So here, this is the QRC extraction window. So where we will mention what are the different extraction type we want to do, whether it is the RC or RC together. And then once we start doing the extraction, the tool will have a look on the individual layers here, and it will do the extraction. And you see this is the small piece where the resistance has been extracted. So once I zoom in, you can see this is the resistance. So this resistance value will be later coded in the this particular netlist. This is about the extraction. So once the extraction is available, extraction is done, we will go for the other view generations, including say timing and other stuff. Now let's focus on the UDFM and ATPG. So as you might be aware from the previous the NXP Connect programs, where people have already explained on the DFT part, how to do the observability, controllability, what is the DFT target. So I will not cover very deep over there. So the intention of this ATPG view is it will allow whether for a given particular cell, for example, whether the inverter input itself got stuck at 0 or stuck at 1, then how we are going to check. So for that purpose, if inverter input itself it will get stuck at 0, it will always produce the output as a 1. So what we have to do, we have to give the input A as a 1, then we have to see whether output is coming as 0 or not. If still output is coming as 1 only, then there is something wrong with the device. So this will be used at the whether the chip got manufactured correctly or not. To test that part, this methodology will be used. So as part of the cell level ATPG information, we do provide this kind of information for that, where we will be using the standard primitives provided by the Mentor Graphics, and we will code the ATPG models. And similar model, we will do it for the AND cell also. However, the disadvantage with the regular ATPG model is it is not sensitive to the what is happening on the internals of the cell. So that is the reason with the updated methodology, we came up with the user-defined fault model with the help of Mentor Graphics, where it do provide the information about all the resistances, capacitances, and we will be modeling those defects as a open bridge, open defect, bridge defects, port open. So on top of using the ATPG, if we use the UDFM based method to do the analysis or to do the DFT analysis, our coverage rate will be further, it will increase, and yield wise it will really helpful. So we this UDFM is something very much coming very important from say example starting from 45 nanometer onwards technologies. Now let's have a look on the timing view. So timing means it do contain all the information about what exactly the functionality area, the different leakage, the power, all sorts of information is modeled as part of the timing. So there are multiple views are possible in the timing, starting from NLDM, ECSM, CCS, noise, AOCV, LVF, CCSP power, electromigration data, aging, all such kind of information we will be providing in terms of the dot-lib timing model. So this itself is a very big domain within the standard cell design, where based on the customer request, we may have to provide lot of PVT points, and we will be very much peculiar on how we are measuring all those parameters. So this is one of the big domain within the standard cell library. So let's have a look on what exactly mean by the .lib. So this .lib do contain the information about functionality, the different arcs possible, the different input capacitance, the delay table, transition table, leakage power, internal power, all such information will be coded in the .lib file. So this there is a library Liberty user guides and the reference manual suite version 2017.6. This is the Liberty standard which is available in Google. And if you get a chance, please go through this. This is because this will act as a Bible for all our development of the standard cell. So for any standard cell, we have to refer this manual and we have to use the proper attributes which has been recommended in this particular PDF. So if you have a look on this particular snapshot here, this is for the one of the inverter. The dot-lib will look like this. It do contain the area information, leakage information, the functionality and other stuff. And going forward, it do contain the delay measurement data, the slew measurement data. And if you have as example flip-flop, there are different sorts of arcs are possible between say clock to D, clock to Q, the different setup time, hold time, the recovery removal checks. So all such measurements, whatever is needed for the top level tools like static timing analysis and other STA tools, we have to code all such information in the .lib itself. So this is the typical .lib which contain the say delay and transition information for different sleeve and load. So index 1 contains the sleeve information, index 2 contains the load information, and for a given particular sleeve and load, what is the value of the delay that is modeled in this .lib. So some basics with respect to STA. So you might have already aware that what is the meaning of setup and hold, and if you don't meet those setup and hold, what are the different steps you have to take care. So all those things have been explained by previous NXP Campus Connect programs. So here the crucial thing over here is for this STA tool to report such violations, it has all the complete dependency on the .lib data, because in the .lib data we do provide the setup time for the corresponding clock and data sleeve, and that information will be later used by the STA tool, and it will perform whether the setup is met or hold is met or not. It will do such analysis. Moving forward, say example, if you consider the between two typical cells A and B, there is some wire is there. So this wire will be represented in terms of resistor and capacitor combination. And as technology shrinks, right, from say 45 nanometer to 65 to 16, so this wire modeling net delay is also being very crucial, as explained earlier also by my colleague Vandana. So that is the reason the PDK team do provide multiple extraction corners only for the wires. So whether we have to ensure like the standard cells gets extracted, and so the analysis has to be performed at the top level with the different extraction corners meant for these wire information alone. So these are the different corners they use for the STA purpose, starting from for the only for the cells, they will vary with the best case, worst case, typical corner. For the wires, they play with all these different combinations. And for the voltage, again, they want to study the complete chip behavior in the different voltage options with the temperature options. So whenever this will be designed at the SOC level specification itself, and that information will be provided to logic library team, and it is our responsibility of the logic library team to arrive at all these PVT conditions. So you can ask me like for a given technology, how many PVT points you might generate. So normally, definitely it will be more than 100 plus PVTs we will provide. So which will be used for the timing closure of the SOC data. Moving forward, I'm at the slide number 83. So this is the different timing models again. So at the very long time back, we were using only NLDM table as example in 140 technology, maybe in say 90 nanometer like that. And going forward, because it had a lot of limitations with the modeling style, we proceeded with the industry came up with new models, basically new formats over here, including CCS, CCSP, OCV, AOCV, LVF, EM like this. So the more the LVF is the most accurate one, which is recommended and which is used in all the lower node technologies. So let's have a quick look on the LVF file. So if you see the right side picture, right here, this is the typical corner where the delay is assume this is the one value it is coming. Let's assume this is a typical corner, and this is the fast corner, and this is the slow corner. So normally, as part of the ST analysis, they use this fast corner for the hold time closure, and they use the slow corner for the setup corner analysis. But if I represent the similar data in a little bit different way, considering the y-axis is the delay, the SS corner will be having one particular delay, and considering all the mismatch variations as explained by Vandana as part of the PDK slide, by considering all those random systematic variation, once we perform the Monte Carlo simulations, we get two values there. One as a late value, one as the early delay value. And that early and late value is exactly what we will be coding in the LVF file as part of the early and late. And based on the further application, whether you want to apply the 3 sigma or the 6 sigma, these values will be getting multiplied automatically by the STA tool, and associated delay values will be getting translated in and analyzed by the STA tools there. But if this variation is not exactly a Gaussian, instead if it is having a little bit skewness, like positive skewness or negative skewness, then we have to go for the moments based information, where this is the one which we are now using for the say for all the latest lower node technologies, which do contain the additional attributes starting from say mean shift, skewness, standard deviation. So these attributes also we have to make it part of the dot lib. So if you get a chance to go through the Liberty manual, which I pointed earlier, that document do contain all this information. Addition to that, we do have a electro migration specific .lib. This do contain the toggle rate information, and it will guide the top level SOC level analysis, that if there are any void or helix happens, assume to catch those things if the tool uses this em.lib as part of the STA, and do the current density kind of estimations. The tool will automatically identify whether in terms of the current flow there is no problem. So there is something called a Black's equation. Generally, people will ask these sorts of questions when with respect to the em.lib, what is meant by MTTF. So this is all about the EM and how the current density equations have been calculated here. Now, once the timing views have been generated, I'm just focusing on one of the EDA view, like Red Hawk. Similarly, we do have other views also based on the target EDA vendor, like Cadence or Synopsys. But here I just focused on the Red Hawk Apache as one of the tool vendor, and that tool will do a different sorts of IR drop analysis in say static mode, transient mode, and dynamic mode. And as part of the standard cell library, we do provide the information like the .cap view, .current view, .pwc view to facilitate that kind of analysis. So let's say I covered quickly on the standard cell library development flow. Now I will quickly cover on the different types of the standard cells, whatever we are using in the flow. So these are the sequential cells we provide, synchronizers, multi-bit flip-flops, and in terms of synchronizers design, we do consider the MTBF formula as a guiding principle to design these sequential cells. Also, we do have combinational cells, the clock symmetry cells, the clock gating cells, then the isolation cells. These isolation cells will help us to propagate the known signal even if the previous domain is shut off basically. So even though the switchable domain is off and we want to translate the known data, in those cases we will be using the isolation cells. Looking at the time, I will not go very deep over here, but yeah, we do also have a different level shifters like buffer type, power, multi-bit O drive with virtual bias pins, enable level shifters, and then the always on cells. So whenever I talk about all these special cells, the Liberty manual do recommend like I should be using a particular attribute to model all these cells as part of the timing data. So this is on the power switch cells, and this is on the retention cells. Then These are the filler cells which will be used to fill the empty area after placing all the cells, and these are the well tap cells used for the eliminating the latch up, and these are the decap and end cap. These decap cells will act as a small battery actually. So whenever there is a IR drop happens, then these decaps will come into play and it will supply the necessary voltages to balance the voltages. And then there are some tie high cells. So example, if you want to permanently connect one of the AND gate input to 0 or 1, assume, then you can't simply connect it as a logic 0, logic 1. Instead, once you translate that information into the synthesis netlist, the tool will replace that logic 0 with the corresponding tie low and logic 1 with the tie high cell. So if you don't use these tie cells, then there will be a short from the VDD to the corresponding gate, and the gate will get damaged. So to avoid that, they will use these tie cells. And these are the antenna cells. Then comes the ECO cells. So these ECO cells will act as a placeholder initially, and later by using the mask change, we can program it to the any other functionality. So, and these are the some guarding cells. If one of your data is very much sensitive and you want to save this data from remaining other signals, so you'll be putting a certain guards over there, right? In the similar way, these guarding cells will protect this victim from the aggressors. Okay, this is on the quick introduction on the different types of standard cells, and I will quickly covering the qualification flow. So we do run different sorts of checks as similar to what Vandana has explained as part of the PDK. So as part of the unit level check, we ensure like all the EDA views, like the left file and those sorts are part, and those are correct in terms of syntax or not. That part we will check. And as part of the consistency check, we will ensure the different views are correctly modeled or not between Verilog and .lib, layout versus schematic, DRC checks like that. And then the integration check is one important thing where we will add all our cells as part of the RTL to GDS flow, and we'll ensure like all the cells are working as per the expectations. And the PPA quantification is one more important area where we will see whether with the addition of the new cells or with the addition of the new architecture, whether we are getting to see the expected power performance area benefits or not. So this is just an overall list, but based on the particular cell and the particular EDA view, the different checks we'll be executing. So that is the end, and as part of the conclusion, I wanted to say like as part of the PDK and standard cell library development, it takes place as part of the foundation design IP. Different companies do have different names for this. Some say it as a design enablement, some call it as a foundation design IP, some call it as a DTCO. There is a different names for that group, but fundamentally this is the group which is responsible for the development of the standard cells, PDK, and also the memory and IO components, and they will deliver that to the SOC design. So the main idea here is the logic library and all these design enablement team will be keeping update with the industry value chain for the product enablement, and across the different technology scaling with the help of AI ML, and those kind of stuff will be incorporated as and when it is needed, and they come up with the differentiating IPs for the successful implementation of the design. So there are vast of opportunities, guys. So basically, we do have just covered the PDK, standard cell, IO, memory, methodology. There are different domains basically within the foundation design IP. These are the key stuff. And if you are interested in these domains, this is a very niche stuff in my view. And you will be having a special knowledge in all these domains, like circuit design, layout design, EDA modeling, automation. If these kind of stuffs are interesting you, then this is the domain you should be trying in my view. Yeah, and these are the fundamentals. Anyway, it should be there, like analog, digital, microprocessor, device electronics, circuits, you should be studying. And the different tools, you should be having some prior experience, maybe the as part of the college laboratories. And this is the automation which we are using normally, like the Python, Perl, Tickle, and the Cadence skill language. Yeah, that's about the overall my presentation, and I would say like this is the very niche domain overall, the VLSI, and I'm very happy to interact with all these new young engineers actually. Yeah. Any questions?